Hello and welcome. This is a presentation on my embedded EECE 2160 collision detection algorithm improvement. My professor is Dr. Jamin Marpaung, and this is spring 2021. And I am Jamin Eisenberg. So the core of this project was to use the DE1 SoC board's VGA port to display free-moving and rotating shapes that could bounce off each other and interact on the screen. I broke this into a couple key steps. Read in from the external keypad, right to the VGA port and to the speaker. The speaker was supposed to make noise when any two objects collided on screen. I also produced a system to represent any polygon on the screen. I implemented an IEEE algorithm for collision detection that I found in a published paper, and then I made an improvement on the algorithm, and I'll talk a little about that more later. And I made the shapes interact with each other with something called collision response, impulse resolution more specifically, and I evaluated my algorithm against the original algorithm. And this whole project was took place in 4 weeks. My system for keeping track of the polygons was as follows. Polygons, which are polygons in the traditional geometric sense. It's a collection of lines that form a closed shape. Polygons contain lines, a vector of lines, and lines are made up of two vectors representing the positions of the endpoints, and those vectors contain x and y coordinates. And those x and y coordinates, so the x coordinates were between 0 and 320, and the y coordinates were between 0 and 240 because that was the resolution of the screen that I was working with. Collision pairs contain two polygons that are colliding, and we know that if two polygons are in a collision pair that they are colliding, so collision pairs can resolve the collision between their two polygons. So the original algorithm uses axis line bounding boxes, which are made up of 2 points that define the limits of a shape. So the axis line bounding box for the shape in the picture is made with its minimum x and minimum y. That makes up 1 point, and the maximum x and the maximum y make up another point. So the entire shape is enclosed within this rectangle. So this requires a big O of n squared algorithm to detect the collisions between all the possible shapes on the screen. For each shape, let's call it I. Then for each shape again, let's call it j. If I is the same as j, they're not colliding because we don't want polygons to collide with themselves. If I and j are colliding, then make a collision pair with them. And I and j are colliding if the x distance between the shapes is less than half of their combined width, or the same thing with y distance and height. So that's how we can tell if two rectangles that define shapes are overlapping. And using that information, we can do more precise collision detection with the lines of a polygon. This is crazy slow, so here's my improved algorithm. The key concept here is that sorting makes everything faster. Comparison-based sorting has a lower limit of big O of n log n time, which is significantly faster than big O of n squared. And this will actually be the limiting time for my entire algorithm. So it should be significantly faster in the long run. The problem can be separated into two subproblems: detecting x collisions and detecting y collisions. And if shapes are colliding in both the x and y directions, we know that they're colliding in general. Shapes can be reduced to intervals. Intervals have a starting position and an ending position, and we can figure out a way to find out if two intervals are overlapping. And so here's the algorithm. For every shape's interval, so in the picture, the intervals are represented with open and closed parentheses. So for each interval, if the interval is at the start of the shape, then we know that a new shape has become active. So we add it to the list of active intervals. And we know that it's colliding with all the currently active shapes, all the shapes that have been opened but not closed. if the interval we're looking at is at the end of a shape, so otherwise, we can remove the start of this interval, sort of the matching open paren, and remove it, and so it gets removed from the active list, so we know that that shape is closed and cannot be colliding with any more shapes. This is significantly faster, as we can see here. Luckily, after all this work, my improved algorithm is faster than the original in literally every case, and something I'm particularly proud of is it is 236 times faster than the original algorithm in the case of 100 X shapes. So here's the plot of the number of shapes I've inserted into the program versus the time it took to calculate all the collisions per tick. And I did this with the CTime library in C++. So over the course of the project, I ran into a couple of issues, the first of which was memory mapping. This one delayed me about 5 days, but it was before I was working on the project every day, so not a huge delay in general. The problem was I tried to access the physical addresses of the machine to write to the VGA port to display things on the screen, and that gave me a segmentation fault because I was not allowed to access those physical addresses. So I went back and reviewed some memory mapping things we talked about at the start of the semester, and I was able to map the physical memory to virtual memory that the system allotted for me, and I just read and wrote from and to there, and that was able to successfully write pixels to the screen. The second issue I ran into was taking this set intersection. So as I described, two shapes are colliding if both their x coordinates are colliding and their y coordinates are colliding, and we needed some way to check that for all the shapes. So this delay took me 2 days, and it was when I was working on the project intensively. So quite a bit of a delay. Part of the problem was that sets in C++ are ordered, and that works out well to speed up their operations, but it means we need a way to order its elements. We need some sort of function to compare the elements in a set. All of the sets in my program were of collision pairs, which consist of two things. They consist of two polygons. So the question I got a little hung up on is, how do you order elements that contain two other elements? And the answer is lexicographically. And what that means, it's a big fancy word for comparing things like they're in a dictionary. First you compare the first two things, and if those are equal, we move on to the next one. And actually, for our problem, we can stop there. So if the first two things are different, we can just compare the polygons, which are compared by IDs, and if they're the same, we can move on to the second ones and compare those, and that will give our final result. An additional problem I had here was that the overriding the less than operator wasn't working. I'm actually still not sure why, so I made a struct to represent the collision pair comparison function and used that to define sets and used that in the set intersection operation. The third issue I ran into was the largest. This was collision handling, and actually this is a problem I still have not solved with this project, which is something I'm not too happy about because I think everything else is pretty complete. The issue is collision handling works sometimes, and I can't tell what differentiates the cases where it works and where it doesn't work. So it's very, very hard to debug. But I'll go ahead and explain my approach anyway, and if you have any suggestions, feel free to leave it in the comments, I guess. So my approach was to calculate the relative positions and velocities between two shapes, and then using their relative positions, I can and their axis line bounding boxes, I can calculate the x and y overlap of the two shapes. If the x overlap is greater, I know that I need to resolve the collision in the y direction. It helps me to think of like a square and a wall. If the square is bouncing off the wall, they're always going to be overlapping way more in the y direction than they will be in the x direction, so the collision is resolved in the x direction because it needs to bounce this way. And so to resolve the collision, we know which direction we need to do that in. We calculate the collision normal, which is which way the collision should be resolved. Then the relative velocity in the normal's direction, and we do that by taking the cross product of the two. If that's negative, we don't resolve the collision because it means that the shapes are moving away from each other. So if we did resolve the collision in this case, we would get some jittering because we just don't want to resolve collisions when it's moving away. And finally, we change the shape's velocities according to their mass relative to the total mass of the collision. So if you get a really big box and a really small box and they collide, the small box will be moving much faster than the large box after the collision, because that's how it works in physics. All right, this is the live demonstration. Here's the D1 SoC board with the external keypad and the speaker that will emit a noise when things are colliding. And right now I have it rigged so that the program will stop when things are colliding because, as I said, collision handling isn't working exactly properly, but here we go. As you can see, we have a whole bunch of different shapes that we can put onto the screen, and the program will stop exactly when we get a collision between the shapes. Just do a couple more rounds. And actually, additionally, we can decrease and increase the mass of the shapes we're inserting, and that will be output to the console. So now I can do some large shapes if I increase the mass. Big shapes. So now we're set up so that collisions will be sort of handled and the speaker will emit a noise when things collide. So here we are. It makes a lot of noises when things collide a lot, but that is working, even though it's a little annoying sometimes. But as you saw with that triangle in the corner, the collision detection, or the collision handling rather, sometimes works. Yeah, so that's the project. That's all. Thanks for watching, and feel free to leave any questions you have in the comments below.